the determinant is a function from square matrices, say, to numbers. So it goes from n by n matrices to, say, real numbers. But more generally, it just depends on the type of entries that you have. So you could say it goes from n by n matrices to 1 by 1 matrices, for example. And it's very powerful and very important, but unfortunately it's kind of confusing to define. So let's just get started with the first case. So here's the definition for 1 by 1 matrices. So the determinant of a 1 by 1 matrix is the entry, is the only entry. Okay, so that's very easy. So this is, in general, they're complicated to define, but for a 1 by 1 matrix, it's very easy. So for example, the determinant of the matrix 3 is simply the number 3. The determinant of the matrix's only entry is -5 is the number -5. Okay. So the determinant of 1 by 1 matrices is very, very, very easy. So in general, to define determinants for larger matrices, we use induction. So we use induction to define the determinant of larger matrices. So typically, so I told you how to calculate the determinant of a 1 by 1 matrix. I can also tell you how to calculate the determinant of a 2 by 2 matrix. So usually you're shown how to calculate the determinant of a 2 by 2 matrix, and then from there say, okay, how do we calculate the determinant of a 3 by 3 matrix from that? But because it's confusing, I decided to actually start even one layer lower. Okay, so the determinant in general is a function that goes from square matrices to numbers. Our goal for right now is just to define this function for an arbitrary matrix, like a 10 by 10 matrix. But to get started, we just define it for a 1 by 1 matrix. So the determinant of a 1 by 1 matrix just spits out the number that, the only number that there is. Okay, so first we need another definition. So here's just a definition. If M is an n by n matrix, then the ij submatrix is the n minus 1 by n minus 1 matrix obtained by removing the ith row and the jth column from the matrix M. So we can, given a matrix, we can get a bunch of smaller matrices by just removing one row and one column. for that matrix. So this is just to get started. So, for example, if the matrix is 2, 3, 1, 5, 7, 6, minus 1, 2, 4. So if this is our matrix M, then there are basically 9 different 4x4 matrices that we can get out of this for each entry. So if we look at the the 1, 1 submatrix is, so if we're talking about the 1, 1 submatrix, then you look at the first row and the first column, and you get rid of that. And so that gives you this 2x2 matrix, 7, 6, 2, 4. That's what the 1, 1 submatrix looks like. We can, you can do whatever you want. We can, what is the 2, 2 submatrix? So then you go to the 2, 2 entry, that's the 7 here, and so we have to remove that. And so if we remove that, what we're left with is, we're left with 2, 1, minus 1, 4. So each of the 9 entries gives us a corresponding submatrix obtained by removing the row and the column that that contain those entries. Let's see if I can just get rid of these. So that's the 2x2 submatrix. We can do the say the, oops, what happened? So for example, the 2, 3 submatrix. So now we have to remove the second row and the third column, and then you have 2, 3, minus 1, 2. So there are 9 of these in total, 9 submatrices in total. Okay, so for each particular entry, you just cancel to remove that row and remove that column that contains that entry. And you get a submatrix. Okay, so in general, if you have an n by n matrix, so if you have a 4x4 matrix, then there are 16 n times n submatrices. For each entry, you can remove the row and the column that contains it. That gives you a matrix, square matrix, 1 dimension lower. Okay, so now that we know what these submatrices are, let me give you another definition. So the cofactor matrix of a n by n matrix, say A, so that's n by n, so it has entry A11, A21, AN1, going across the top, A1N, here you get ANN, is the matrix which just is written C, and whose ij entry is -1 to the I plus j times the determinant of the ij submatrix. Okay, so the cofactor matrix of a n by n matrix it's still an n by n matrix, but it's obtained by calculating determinants of smaller dimension matrices. So the cofactor matrix of that. So let's just do an example so we can see how that works. So example, let's take a 2x2 matrix. So say A is, so I'll just use different symbols now, A, B, C. D. Okay. So the cofactor matrix, what's that going to look like? It's also going to be a 2 by 2 matrix, and so we have to do a bunch of things. So to find C, first we have to say that what is C? So C1, 1, well, what is that? That's going to be negative 1 to the 1 plus 1 times the determinant of the 1, 1 submatrix. So if you delete the first row and the first column, you just get the number D. C1, 2, so that's negative 1 to the 1 plus 2 power times the determinant of the 1, 2 submatrix. So that means you're going to delete the first row and the second column. So if you remove the you remove the first row and the second column. So that gives you the element C. And sorry for using okay, whatever. And then C2, 1, so that's going to be negative 1 to the 2 plus 1 times the determinant of, so if you delete the second row in the first column, you're just left with the entry B. And then C2, 2, that's negative 1 to the 2 plus 2 times the determinant of, if I delete the second row and the second column, I'm just left with that thing there. Okay, so sorry, let's look at the definition. So the cofactor matrix is obtained by, so the entries are given by the summation, so the ith j entry is negative 1 to the I plus j times the determinant of the submatrix. So in a 2 by 2 case, it's very easy. So the cofactor matrix of A, so that's capital C, looks like, well, it's 1, 1 entry is negative 1 to the 1 plus 1 times the determinant of D, so that's just D. And its 2, 1 entry is negative 1 to the 2 plus 1, that's negative 1 to the third power is negative 1, so that becomes negative B. Its 1, 2 entry is also going to be negative C, and its last entry will be positive A. Okay, so in order to calculate this, I had to know, in order to make sense of this definition, you have to understand the determinant of a smaller dimensional matrix. So we haven't yet defined what the determinant of a 2 by 2 matrix is, but we already know what the determinant of a 1 by 1 matrix is. It's just the number D. So this is just the number D itself. And similarly for all these others, the determinant of C is just the number C itself. And the reason there's a negative, where does the negative come from? The negative comes from this thing here. Okay, so that is an example of a cofactor matrix. Now we can't do any other examples because we don't know how to calculate higher dimensional determinants. But the point is that we use these cofactor matrices in order to inductively define the determinant of higher dimension matrices.